So let's look at an example of a problem in one dimension for spring force. So let's say we have a block, it's being suspended from a spring that's attached to the ceiling. If we know that the spring has a spring constant of 0.2 newtons per meter and it's being stretched 5 centimeters from its equilibrium, what is the mass of the block? So we're going to go ahead and implement our problem solving method using that acronym we've talked about before, FIDESA. So F is for find. What is it I'm trying to find? That would be the mass of the block. So mass of the block. The I in FIDESA is an image. So we're going to essentially draw a diagram of what's going on here. So the label that or draw that as like the ceiling. The spring is being attached from the ceiling and it's being stretched a little bit because it has some mass hanging from it. And this would be the mass of the block. And we can even denote, let's say that this is its equilibrium position. We could call X naught. It's being stretched some distance away to, we'll say X1, where that distance is the 5 centimeters. Now, because our spring constant is in newtons per meter, because also mass of the block is going to be denoted from the force, we need the 5 centimeters to be translated to meters. So we know that this is now being stretched 0.05 meters. And the next letter in the acronym, the D in FIDESA, stands for data. And that's just going to be all the numbers that they give me. So the spring constant, K, is equal to 0.2 newtons per meter. The change in position or the amount it's being stretched, I could just call X or I could call delta X, totally up to you. But this is just going to denote the distance from equilibrium that it's being stretched. That's the 0.05 meters. And that's it. That's all we know for the data points. The next letter in the acronym FIDESA is E. E is going to stand for equations, and this is all the equations that I know I need or I think I might need to solve this problem. For starters, we need to know that the force, essentially, or the net force, is going to be equivalent to all the sum, or the sum of all the forces. So we're just adding all the forces together. We're going to have two forces here for this. We're going to have the spring force, that's what's holding the block up, so Fs, and the force of a spring is equal to the spring constant times the displacement distance, how far it's been stretched or compressed from its equilibrium state. You can think of the equilibrium state of the spring as being when I have neither pulled or pushed on it, it's just there, neutral, no force is acting on it. And then the other force would be gravity. Gravity is going to pull the block down. Maybe we should have specified for this practice problem that we can assume that the spring is weightless, essentially, or at least in comparison to the mass of the block, but it's not playing a role here on the gravity pulling the block down. So the force due to gravity is equal to the mass of the block times gravitational pull. And then we just kind of set up our equations here. So the next letter in our acronym is S. So FIDESA, S for solution. This is going to be our algebraic solution. I'm going to take, you can take this one of two ways. We can denote the direction in the acceleration, or I can denote the direction in the forces. So if I denote the direction in terms of the forces, I'm going to take the acceleration to be a positive 9.8 meters per second. I'll show you what I mean by that in a second. Let's assume down is negative and up is positive. That means my net force, again, being the sum of all the forces, is going to be positive. What's pulling it up? That's the spring force. So that's a positive force. So plus Fs. And then I'm going to add to it the gravitational force. And that, if it's pointing downwards in the downward direction, it's going to be minus Fg, yeah, the gravitational force. So that's just going to look like Fs minus Fg. Now, if the block is being suspended, it's not moving, therefore it has no acceleration. That means that that's equal to 0. So then that also means that my spring force is equal to my gravitational force if I just added gravitational force to both sides. I can then use what I know about spring force, gravitational force. So that means I have the spring constant, the displacement of how far it's being stretched. That's equal to the mass of the block times gravity. And what am I looking for? I'm looking for the mass of the block. So I'm going to divide by gravity by both sides. I get that the mass of the block is equal to the spring constant, how far it's being stretched from its equilibrium, divided by the gravitational pull. And that's my equation. I'm done at that point in terms of my solution. The last letter in our acronym A by DESA is answer. And that's just where I'm going to plug in my numbers. So this means that I have 0.2. Instead of writing newtons per meter, so we can check that all our units will actually cancel, I'm going to write kilogram meter per second squared, because that's what I know 1 newton is. So off to the side here, we can maybe denote, maybe up here, 1 newton is equivalent to 1 kilogram meter per second squared. And I want mass, so the only unit I better have left is kilograms. So let's make sure that that's what we get. So I get 0.2. This is kilogram meter per second squared. It's a newton per meter, so that's divided by a meter, times the displacement, so that would be times the 0.05 meters, all divided by gravitational pull, so 9.8 meters per second squared. As mentioned before, this should be positive because I already took into account the direction when I made gravitational pull going down, the force negative. So I don't need to account for it 2 times because that's all that negative means. It's just denoting direction. In this case, I have these meters canceling. I have a meters per second, or maybe we could even do it this way so it shows better. These meters cancel with these meters. This meter per second cancels with this meter per second. I am just left with kilograms. So it looks like everything turned out fine. And I get that the mass of the block should be 0.001 kilogram. Or, because that's so small, I could denote it in terms of grams too. If I multiplied it by 1,000, I get that this is essentially 1.02 grams. Either would be an appropriate way to answer that.